Okay, let's restart, and our next speaker is Andrea Antinucci.
So let me thank the organizers for inviting me to talk. Today I will tell you about this paper that came out last week, collaboration with Francesco Benini and Giovanni Rizzi. Please stop me at any time if something isn't clear. So this story starts from a quite old and well-known observation that one possible physical interpretation of topological quantum field theories is in terms of models for quantum gravity. Indeed, to get a generally covariant theory at the quantum level, broadly speaking, you have two options. Either you introduce some theory which depends on a metric, and then you sum over all possible metrics, or you never introduce a metric. TQFTs achieve general covariance in the second way. Of course, there are sort of weird and exotic theories of gravity, where you don't have a semi-classical expansion in terms of weakly interacting gravitons, and you may want to think about them as sort of confined phases of gravity. What is probably less appreciated, however, is that this is not really enough to get a theory of quantum gravity, because you should also give independence on the background topology. And again, you have two options. Either you sum all possible topologies, or you use some special type of TQFTs that don't even depend on the topology. These are sort of trivial TQFTs, or in a technical sense, they are invertible TQFTs. And there is a general way that I will use to construct these invertible TQFTs, which starts from a non-trivial, non-invertible TQFT of some special type. These are TQFTs that admit some gapped or topological boundary conditions. These boundary conditions are specified by declaring that there is a maximal set of mutually local objects that can simultaneously terminate on the boundary. It's called technical Lagrangian algebra. And this has also the property that it's a sort of anomaly-free theory that you can gauge, and being maximal, you will get a trivial theory after this condensation. And so the resulting theory is an invertible TQFT, and for a reason that will be clear, I will use this kind of construction of these theories. TQFTs with topological boundary conditions recently received a lot of attention in the context of this slab or sandwich SymTFT construction that we already heard two talks this morning, and we will hear much more during the weeks. So since this will not be really the setup that I will use, I will not review it. I just want to emphasize that this is a construction which encodes all possible symmetries of a d-dimensional quantum field theory in a d+1 dimensional quantum field theory, topological quantum field theory. And the all important thing is that it has a canonical construction starting from the input data of some symmetry in d dimension. You construct canonically this TQFT in d+1 dimension associated with the symmetry. And here, it describes the aspects of the symmetry of any TFT with a given symmetry. I just want to make another comment that will be important for us, that until very recently this construction was restricted to finite symmetries, but earlier this year we made progresses in extending it to continuous symmetries. And the basic idea is extremely elementary. You just have to include some type of different, let's say, TQFTs, which are a bit beyond the usual framework of TQFTs because they have infinitely many operators. In the simplest example, if you want to describe a U1 preform symmetry, you just write down this BF type theory, where, however, at least one of the two gauge fields, instead of being a U1 gauge field, is an R gauge field, so it doesn't have large gauge transformation, and the corresponding operator has continued labeled. And in this way, you can describe this U1 symmetry. I will keep using this notation in which small case letters describe R gauge field, while uppercase letter U1 gauge fields. So as I told you, I don't want to use this lab construction. There will be no sandwich in my talk. I want to use the TQFT that are usually used in this lab construction, but in a different setup. I will discuss an holographic setup in which I will put my TQFT on a manifold with a unique boundary, and I want to put some non-topological boundary condition on this boundary. And on the other hand, the Lagrangian algebra that usually defines the topological boundary in the slab construction now is gauged in the bulk. And in this setup, I want to establish a full-fledged holographic duality, which I want to equate the partition function of this TQFT in the slab with this non-topological boundary condition, here this calligraphic B is a boundary value of some gauge field, to the partition function of some dynamical QFT living on the boundary, and I want to determine which is this dynamical QFT. Okay, so is this step clear? So, you might be very skeptic about what I told you so far, because in holography, there is a very well-known correspondence between the stress tensor of the boundary theory and the graviton in the bulk. But while the first is present here, the second is not. So what's going on? Well, there is at least one context in which the objection that I just told you has a clear loophole, and it's the context of the Chern-Simons WCW correspondence. Indeed, the stress tensor of the WCW model as a Sugawara construction is not an independent operator, but is a composite of the currents. And for holography, the currents are dual to the gauge field in the bulk, and so there is no puzzle. We really don't need to have dynamical gravity in the bulk to describe this correspondence. And so if the scenario that I'm going to present has some chance to be true, the quantum field theory that we get on the boundary cannot be completely random quantum field theory, should be of some very special type, which are completely determined by the symmetry. And indeed, let me make one other remark. So, let me emphasize the difference, again, between this holographic setup and the symmetry TFT setup. In the symmetry TFT, the physical theory living on the boundary can be any TFT with a given symmetry, and the TFT in the bulk is only describing aspects related with the symmetry. On the other hand, in the holographic setup, the QFT on the boundary is completely determined by the bulk and the topological, non-topological boundary conditions, and the bulk theory knows everything about it. Okay? So as I told you, then the quantum field theory must be some special type of quantum field theory, which should be completely determined by the symmetry. I will focus on continuous symmetries, and there is a very natural candidate for this, which is the universal effective field theory that describes spontaneous symmetry breaking of this continuous symmetry. So this is indeed canonically determined by the symmetry. If you give me a symmetry, there is a universal theory that describes, is the Goldstone theory that describes the effective field theory for the symmetry breaking. And so this theory has the same input datum as the symmetry TFT. So it's not weird that the two objects, even though they appear to be completely different, they are related somehow. And what I'm proposing, and I will show you in many examples, that the relation between the two is holography. Okay? So if there are no questions, I can go to the examples. Let me start just explaining the main logic that you use to prove this kind of holographic duality in a very simple example. The answer is essentially already known since 30 years. I just want to put it in this context to explain the main methods so that I will not repeat it in the other examples. So this is the simplest example of a U1 zero-form symmetry in D dimension. So this is the symmetry TFT. B here is an R gauge field. So we put it on a manifold with boundary. We endow the boundary with a metric. And we want to write down these non-topological boundary conditions using the Hodge-Star operator of the boundary. And to do that, we also need to introduce a scale, R. Well, to get a good variational principle, we also need to add this boundary term. And now, with this boundary data, I can compute the partition function of this setup and show that it's equal to the partition function of some QFT living on a boundary. The technique, for simplicity, I will take my manifold to be the product of a d-dimensional ball times S1, and then I compose all my fields into the time part and the special part, which is denoted by the tilde. If you plug this back, you will recognize that the time part will appear linearly. You can perform the path integral over the time part, and you will get these constraints that you can solve introducing lower form fields. Then you plug it back, and you will discover that the path integral reduces to the path integral of a boundary theory, written in terms of these two degrees of freedom. Phi naught is a scalar, and omega is a d-2 form, with this action that in this form is a kind of ugly action. So it's not manifestly covariant, and in particular is linear in time derivative, as you see. Here, sorry, I haven't told you, but when I write down these boundary conditions, this calligraphic B is a fixed field on the boundary, which plays the role at the end of a background field for the boundary symmetry. But here is a boundary datum, it's a fixed field. So here, just to get some intuition, you can ignore it for a moment. This action is linear in time derivative, and whenever you have actions linear in time derivative, the path integral should be thought as a phase space path integral. And as usual, we can integrate out momenta and get a the configuration of space particular. If it is, here you integrate out omega 2, you will get this action, which is just the action of a compact boson coupled with a background for the shift symmetry, which is indeed what we expected. Actually, this is not completely true, because if you paid attention to how I solved the equation in the bulk, there was no possibility for introducing a winding for this boson around the time circle. And indeed, there is a missing ingredient with respect to what I told you at the beginning, that to really get a full-fledged holographic duality, we also had to gauge this Lagrangian algebra in the bulk. I will not explain the technicalities, but essentially to do that, you have to insert defects in the bulk and repeat the computation, and you will understand that if you insert some defects, some Wilson line of the gauge field A here, what you will get at the end is the same action, but where phi now is a fixed winding around the time circle. So when you sum to reconstruct this gauging, you will reconstruct the sum over windings, and you will reconstruct the partition function of a compact boson. Okay, so these kind of abelian examples can be generalized in a variety of ways. Of course, you can consider higher form symmetries, for instance, for p equal to 1. Needless to say, on the boundary you will get a photon, and in general you will get some generalized Maxwell fields. We can add chiral anomalies, we can consider abelian two groups in 4 dimensions, or this non-invertible chiral symmetry in 4 dimensions. I don't have time to discuss all these examples, I just want to focus on the last one. And I will not give you the details, because the details are very similar to the examples that I just discussed, they're just more complicated, but I want to discuss some consequences of this. So, just a brief reminder, as everybody knows, in 4-dimensional QED, master's QED, there is a classical symmetry, the axial symmetry, which is broken quantum mechanically by an IBJ anomaly. But what these people recently showed is that you can do slightly better, because the defects, which are labeled by rational numbers, can survive quantization at the only price of becoming non-invertible. And earlier this year, we determined the symmetry TFT for this symmetry structure. It contains a piece describing the zero-form symmetry, that would be U1 symmetry, that will become the non-invertible one. A piece describing the magnetic symmetry of QED. And then there is an interaction which is responsible for the non-invertible structure. Okay? Because of this last term, the gauge transformations are very complicated, as you see here. You should not read the whole formula. I just want you to focus on this fact that the gauge transformation acting on A1 also acts on G2 in this way, where also a dynamical field F2 appears. So this will be very important, as you will understand in a moment, because at the end I want to get a boundary theory, and this fixed field, this calligraphic B and calligraphic H, I would like to think about them as background field for some symmetry on the boundary. But in order to get this interpretation, I should be able to assign to these fields some gauge transformation in such a way that the boundary condition is gauge invariant. However, since rho naught is also acting on G2 in this way, you can see that there is no possible gauge transformation that you can assign to H2 that reabsorb the gauge variation of this. So the only option that you have is to freeze rho naught on the boundary, and therefore B1, which would be the field that shifted with this gauge transformation, should not be thought as a background field for any symmetry on the boundary. As you will see in a moment, this is really the hallmark of the non-invertibility of the symmetry.
Question?
Yes?
Can you summarize which field lives in how many dimensions?
So,
just remind us, which field is in how many dimensions? Which one is dynamical and which one is classical?
oh, here all these fields are dynamical. The only classical field is B1 and H2. The calligraphic B1 and calligraphic H2 are background fields. All the other fields, both the lowercase letters and the uppercase letters, are dynamical.
In how many dimensions do they live? In 5 dimensions?
In 5 dimensions, yes. B1 and H2, on the other hand, only live in 4 dimensions. So if I repeat the same logic that I told you before, in the case of a compact boson, in this case you will get a particle over 2 degrees of freedom, A1 and phi naught, with a boundary action that contains a compact scalar, a photon, and this axion term. This theory is often called axion-Maxwell theory, and it was indeed suspected to describe the spontaneous symmetry breaking of this non-invertible chiral symmetry, and here we are confirming this expectation. However, referred with what I told you a few seconds ago, Here, while H2 can be thought as the background field for the magnetic symmetry, this is like standard coupling, B1 is not the background field for the non-invertible symmetry. Indeed, there is no gauge transformation that you can assign here to B1 that makes this action gauge invariant. On the other hand, you can turn on B1, and you should turn on B1, because holographically, this is the search for the operator d phi naught. But you should not think about it as a background field for the non-invertible symmetry. Indeed, it's likely that there is no sensible notion, cohomological notion of background field for non-invertible symmetry. We have good homological notion in terms of insertion of defects, and good cohomological notion in higher dimensions, say if you have some symmetry TFT attached or some holography attached. But purely from the boundary point of view, there is no sense in which this B1 can be thought as a background field. So now I want to go to a couple of non-abelian examples, if there are no further questions. So I guess that now everybody of you has a guess for what's the answer for this. So now I'm discussing the example of let me just focus on 4 dimensions, since the next example is really tied to 4 dimensions, but this example here, you can discuss it in any dimensions. So we take a non-abelian symmetry G, and the symmetry FT for this was already conjectured in these first 2 papers, and then better discussed in this other one. It's written in terms of a G connection A, and B3 is a tree form valid in the Lie algebra. It's a section of the adjoint bundle, so it transforms in this way under gauge transformation. Needless to say, here the computation will be much more messy, but you can show that with the suitable gauging of a Lagrangian algebra, this theory turns out to be the holographic dual of a sigma model with target space given by G. So if G, for instance, is SUN, you might want to call this the pi Lagrange and describe the dynamics of the Goldstone boson for the spontaneous breaking of SUN. And of course, you can also add the chiral anomaly. In the box, this is nothing but adding a 5-dimensional Chern-Simons term. If you repeat the computation, this will give you a WCW term on the boundary. Here, let me remark that I'm presenting the formula with the background turned off, but of course you can turn on the background, and this also provides an effective method to determine the form of the gauge WCW term in any dimension. It's kind of complicated, but you can do it. Actually, the interesting example that I want to discuss is the one of a non-abelian 2 groups in 4 dimensions. It's a symmetry structure that mixes a 0-form non-abelian symmetry and a U1-1 form symmetry. And as far as we know, there was no general proposal for what is the Goldstone theory for this symmetry structure. And so we can do it if you buy our proposal. The symmetry TFT was not explicitly determined in our paper from January, but it's a simple application of this. It contains a part describing the 0-form symmetry, a part describing the magnetic symmetry, and then there is an interaction with a coefficient k that is responsible for the 2 group. Again, we can repeat all this computation, and with a suitable gauging of the Lagrangian algebra, you can show that this is the dual of a boundary theory that contains a sigma model with target space G, a photon, and then there is an interaction between the photon and the pions, which takes this form as a sort of Chern-Simons WCW-like term. And I want to discuss the interpretation of this term in a specific model to explain how you should think about it. So the model that I want to discuss is a gauge theory with gauge group UN and F flavors of massless Dirac fermions in the fundamental, so it's UN QCD. So this theory has a chiral symmetry, SUF left and SUF right. And well, what do we know about this theory? Of course, there is a non-abelian sector that will go to strong coupling, and if we have low enough number of flavors, the chiral symmetry will be spontaneously broken and we'll have pions. Also, the abelian sector will remain weakly coupled, so at low energy we'll still have a photon, and the magnetic symmetry is also spontaneously broken. However, since the photon is interacting with the quarks in the microscopic theory, there is no reason why at low energy the photon should be decoupled from the pions. Indeed, we can determine the interaction between the 2 with what we determined in the slide before. Indeed, if you, at least you read the paper on 2 groups by Cordova and Dimitrescu in Trigator, you will recognize that this theory has a non-abelian 2 group because there is a gauge flavor anomaly. And so there is a non-abelian 2 group mixing the flavored symmetry and the U1 magnetic symmetry. This has coefficient k, and because of these two bullet points, these two groups is completely spontaneously broken, and therefore, at low energy, the effective field theory should contain this term that I just told you. It also contains a standard WCW term because there is a pure cubic anomaly for the flavored symmetry. But here, this term has a very simple interpretation. Indeed, if you look at it for a couple of seconds, we recognize that this is nothing but the baryon current. And this is the standard coupling of a U1 gauge field to the baryon current. And indeed, in this model, to get U1 QCD, we started from SU1 QCD and we gauged the baryon number. So it's kind of natural that at low energy, this coupling should appear. Also, precisely for this reason, so the baryon number has been gauged, so we expect the baryons to become not gauge invariant, of course. And indeed, you can define the baryon as disordered operators. And similarly to monopoles operator in Church-Simon's theory, because of this term, which is a kind of Church-Simon's term, these baryon operators will get a gauge charge under the U1 gauge symmetry. This gauge charge is M. And also as a consequence, just a trivial consequence here, if it was not for this term, because of this gauge field here, we also could have an emergent U1 electric one-form symmetry in the infrared. But because of this term, this is broken to the Gn subgroup. And why is it so? Well, because the Wilson line of charge n is screened by a baryon, which is now not gauge invariant. So if there are no further questions, let me summarize. So I think the main take-home messages of this talk is that if you want to think about symmetry TFTs not inside a slab, but in this holographic setup, you want to think about them as holographic dual of some theory. They are the holographic dual of these universal theories describing spontaneous symmetry breaking. And the fact that these effective field theories are universal is mapped to the absence of dynamical gravity in the bulk. So I think a general lesson is that we should think that this absence of dynamical gravity, when we take holographic duals which are TFT, we are describing universal aspects of the boundary theory. And we are describing here, indeed, the spontaneous symmetry breaking, which is universal. So there are a couple of interesting open questions that maybe are hard to answer, but I think it's interesting to ask them anyway. I haven't emphasized it during the talk, but many of the theory that we get are interacting and generally non-normalizable theories or sigma model, which are varied only up to some scale. And of course, we understand it very well from the boundary point of view, but I think it would be nice if there is also a bulk understanding of this, a TFT understanding. Presumably, it is because of the non-topological boundary condition that we defined, that at some high scale, it should lose sense sometimes, but we don't really have a very good understanding of this. And also related with the second point, so you can imagine, for instance, to have a concrete RG flow with an holographic description in which at low energy you have symmetry breaking and you will reduce to the universal theories. So at low energy we expect, indeed, from our results, to have this holographic dual which doesn't have dynamical gravity. But if you go a bit beyond universality, you start introducing irrelevant operators, and at some point you integrate in other degrees of freedom. You're going beyond universality, and so we should not expect this to be captured by any TFT. We should expect dynamical gravity to enter again into the game in holography. And if we can find some concrete example, maybe this could teach us something about how this mechanism happens from the point of view of gravity. Because as I told you at the beginning, this TFT thought as theory of gravity should describe some confined phase of gravity. So if you reintroduce dynamical gravity, this gravity becomes deconfined, and maybe we can use this to understand how this happens from the bulk or the boundary point of view. So let me conclude here. Thank you.
Questions?
I have two questions, actually. The first is, you mentioned at the beginning that your holographic setup is different from the symmetry TFT. One thing that I don't understand is when you say that, elaborating on what's the difference, like asking, if I have the Lagrangian subalgebra and I impose Neumann boundary conditions in the sandwich setup and then I close the sandwich, am I not gauging the symmetry?
Well, okay, let me first answer the first question, then maybe you can repeat the second because I've not got completely the question. But so the main difference between the two scenarios is that in the symmetry TFT, the dynamical QFT that you put at the boundary can be any QFT with the given symmetry. It's not determined by the bulk. Okay? While in holography, I'm putting my theory on a manifold with a unique boundary. I specify the non-topological boundary condition, and this gives me really a duality between the bulk and the boundary. So there is a dual description.
Yeah,
the boundary theory is completely determined.
The difference that I'm asking is with what do you mean by gauging the Lagrange algebra, and what is the difference with respect to imposing non-boundary conditions in the sandwich?
Okay. This is not indeed a very big difference in the sense that the same Lagrangian algebra that you usually use to determine the topological boundary condition in the sandwich construction is something that you can gauge in the holographic setup. It's just that in the holographic setup, it's more natural to not have two boundaries.
Yeah.
But it's just that. It's just a formal difference. It's not really a conceptual one.
Okay, thank you. And then the second question that I have is when you mentioned that you lose the how the background gauge transformations look for your curly B, and then I shouldn't interpret it as a background gauge field. Is there a big difference between the continuous case and a finite symmetry?
You mean non-invertible finite symmetries?
Yes, for example, like, or more precisely, I'm thinking of when you gauge a subgroup, a finite subgroup, like say in the C4 of S-duality in your paper. So
maybe I've not understood the question, but what I was emphasizing here is that in this case, the symmetry for which B would be the background field is a non-invertible symmetry. Mm-hmm. And this is the reason why B loses its interpretation as background field. For normal invertible symmetries, there is no such an issue. For instance, here H2 is really the background field for the U1 magnetic symmetry. There is no issue. And this is the same for finite or continuous symmetry. There is no difference about the two. The difference is invertible versus non-invertible.
Okay.
You have a question? So if you have like a Goldstone theory, no, you can talk about higher derivative corrections.
Sorry, can you repeat?
You can talk about higher derivative corrections, no? And I would expect that you should be able to incorporate this in this description in the sense that you should be able to modify this boundary condition a bit so that...
I don't think so. Indeed, this was related with the last point. I think that if you're describing a full theory with an holographic dual, when you start introducing higher derivative correction, I would expect that dynamical gravity should enter again into the game to have an holographic description. I don't think that higher derivative correction can be captured by a TQFT.
Of course, there will be some coefficients that are not fixed. But
honestly, I'm not sure. I have not analyzed the problem. It's just my opinion, but we can discuss about it.
Also, another thing. So here you discuss this boundary condition, which like break completely the symmetry. No, that's the idea. But maybe in some physical setups, it's more useful to find boundary condition which like break partially, like when you have mixed anomalies and so on. You know what kind of things you have to find those Goldstone theories.
We don't know. We thought about it for a bit. I mean, for instance, you can have breaking from G to a subgroup, and it might be that you can write down some other non-topological boundary condition that does the job, but we don't know. We haven't analyzed it.
Okay, if there's no further question, let's thank Andrea.